We were, so yesterday, um, we were, um, I guess we want to be here. I don't want this. And, oh, well, there was some discussion of the exams. So if your class, so here's the exam schedule, right? So if your class meets like here, then it's Thursday, the 17th from 10 to 12. Okay, so maybe I'll put that in the chat. Um, okay, Kelly took over yesterday. Huh? Good for you, man. Uh, so yeah, the final exam is Thursday. It says here, December 17th. So that's a week from Thursday. Um, a little hour earlier than usual, right? So 10 to 12, and I'm open to keeping it, you know, going a little longer than that if you need that. So um, let's that's the official time though. The problem with going longer is that some people may have a conflict. So if you have a conflict, let me know and we'll try to accommodate that somehow or other. Um, all right, so uh, there's this thing going on with the sun. Have you followed this? This could be causing more internet outages. Um, there's a big solar flare in more than 3 years, biggest in more than 3 years. I just made it bigger. Whoa, it's getting bigger and bigger as we speak. Oh my gosh, solar flare. I think the sun is pretty cool, huh? No, it's hot. Okay. So yeah, let's go back. Um, yeah, I'm just gonna leave that page. And did I save that? I think I saved it. Yeah. So should I make sure? So to be sure, if you didn't get to the chapter 6 test because of some sort of snafu, um, let's make sure that this actually took, because I had some trouble with saving things. And so it says now, oh, um, yeah, due tomorrow before class. Okay. So here we are, week 15, Tuesday. And we left off yesterday talking about hyperbolas. Um, and here's the work that we were doing before I was so rudely interrupted by an internet dropout.
Excuse me, Professor. I'm so
Yeah,
sorry to interrupt.
no
Um,
worries.
I just had a question about the final. Is
Hmm.
is it going to be cumulative or
Yeah, that's sort of a requirement, I think, of the college that we have a comprehensive final exam. And by comprehensive, they mean cumulative. So covering all the topics. And I know that seems a little daunting because what did we do? We did geometry, we did functions, we did trigonometry, and then we did conic sections and tried to, show that it's all connected at that stage. I think I kind of need to zoom out a little bit. Um, so that zooms the other way.
It's not going to be on open math, right? The final.
I was not thinking no.
I have a
Um,
hard time with my open math. I think that's
okay.
why I was
All
asking.
right, I'll take that into consideration and say no. We'll just have a regular pencil and paper final.
Okay.
Yeah. Okay, so we were dealing with, and any other questions? Yeah, so there's a comment, the college doesn't require it. I'll look that up. My recollection is that they do require it, but many professors just ignore that. Which, what's the penalty? Uh, um, but maybe I'm old fashioned. Maybe that was a requirement that was dropped back in 1952 when I was, you know, in mid career. Um, so yeah, I'll look into that. Maybe I'll ask around. Uh, you know, so are we going to have a separate test on conic sections, you might ask? And, you know, I would say that, you know, if we were to just test on conic sections, we could make that fairly comprehensive, right? And solving triangles, right? So the chapter 6 and chapter 11, just those two chapters kind of cover. I mean, we could have even a little proof in there, right? Prove that the circular angle is half the central angle subtended by an arc, right? I think we talked about that a little bit yesterday. In fact, yeah, that's exactly what's here, right? We didn't show the proof again here. We used the result, but we kind of showed the proof in a way, right? What does that look like? Well, do we have time for that? Maybe. Do I have my compass? It's fallen to the ground. So the claim is just sort of in the way of review, huh? The circular angle subtended by an arc of a circle is 1/2 the central angle subtended by that arc. And I think a little diagram is apropos here. And I'm going to do the special case where the circular angle is, so here's the center of the circle. The circular angle is includes what one side of the circular angle is a diameter of the circle, right? So this is R and this is R, and this is the arc subtending this angle here, right? So this is arc, let's say A, and we're in a circle of radius R, and we can say, let's label the vertices here. So this is also R, right? So this is O, let's say, this is A, this is B, and this is C. Okay, so we wish to, so we want to prove that angle BAC is 1/2 angle BOC, right? So if this is theta, then this is theta over 2. And I think we could say that AO equals BO, and that's because they're radii of the same circle. And so that means that triangle BOA is isosceles by definition. So I'm doing kind of a paragraph proof here, right? And we know that angle BAO then is congruent to or equals in measure angle ABO because the base angles of an isosceles triangle are congruent. You can use this symbol for congruence there. Okay, so we can say this angle here must also be this angle here, which I'm sort of prejudicing the issue by labeling it as half of this, right? So that I don't mean to assume. So maybe I should erase this, right? So we want to demonstrate that that angle is in fact theta twice this angle here, right? So we know that angle BOA plus angle, well, can I say, since I've labeled that theta over 2, kind of prejudicing the issue, but I haven't assumed that's true, right? So that must be equal to pi radians, or 180 degrees. If you wanted to go in degrees, that would be all right too. So that says that theta is equal to, just combining like terms here, pi minus angle, the radian measure of angle BOA, right? But we know that since angle BOC plus angle BOA is equal to pi, that's just because it's a straight angle, right? So pi or 180 degrees, pi radians. And so that means that BOA BOC is equal to pi minus BOA. All right, and that's just by the subtraction property of equality. Just subtracting the same thing from both sides, right? And then things equal to the same thing are equal to each other. So are we there yet? Yeah. So angle BOC is equal to theta by the transitive property of equality. Transitive, things equal to the same thing are equal to each other. And that's what we were trying to show, that, this is theta. Okay. Now that's a special case where, A is opposite, or one side of the angle, the circular angle is a diameter of the circle. The thing is, you can always take an angle and, divide it into pieces for which that's true. So if I had an angle BAD, oh, that's not bad. No, it is bad. Angle BAD. So this would be, if this is alpha, then we could, so by the same argument, this would be half of alpha, and the sum of these would be the sum of, well, the sum of these would be half the sum of those, right? And so that would be the more general case. All right, so let's go back to, so why was that appropriate here? Oh yeah, there was a problem on the exam, right? So right, that was number 3, which I guess if you didn't get it right before, you can get it right now. Okay, so so then we went to the textbook 5.4, number 12. We wanted to graph this hyperbola, and we did, right? And how did we do it? We said, look, the transverse axis goes from negative 3, 0 to 3, 0. Here's negative 3, 0. Here's 3, 0. Those are the x-intercepts, right? If y equals 0 in this equation, then x squared over 9 equals 1, which is true either at x equals negative 3, whose square is positive 9, or x equals positive 3. And then we find the focus is way out here. So I mean, it's outside of the paper. Or I guess there's another one back over here, but it would be way out here, right? So I didn't really accommodate space for those. The asymptotes are It's going to be b over a because a is with x. Right? You think of delta y over delta x as being the slope, and if a is with x, then it's b over a. If a is with y, then it's a over b. Okay, so it's and a is 3 and b is 8, so b over a is 8/3 plus or minus 8/3 gives you these two asymptotes. And okay, that was that graph. Then we had this is what we were doing when we were so rudely interrupted, which was saying, look, here's the Pythagorean identity. The sum of squares equals 1. If you divide through by cosine squared, you get an equivalent equation. 1 plus tan squared equals secant squared, right? This is 1, this is tangent squared, and that's secant squared, which then you can say, well, secant squared minus tangent squared is equal to 1. So here you have a difference of squares, and that's what we have with a hyperbola, right? So this is, what you use for an ellipse. And this is what you use for hyperbola. And so if we want to sort of match these, right? So if it's secant squared minus tangent squared is always equal to 1 for any angle. This is an identity, right? Doesn't matter what angle theta you put in there, that's always true. So if we want this to then use this to parameterize our hyperbola, then we'd say, well, if this term is secant squared and this term is tangent squared, that means that x is plus or minus, or let's just take plus, right? The positive 3. I mean, you could take the minus as well. And same thing down here. For simplicity, let's just take plus. So x is 3 secant theta, y is 8 tangent theta. If I were to plug those into this equation, what would I have? I'd have 3 times secant theta squared over 9 minus 8 times tangent theta, right? This is x squared over 9. This is y squared over 64. And that's going to be 9 secant squared theta over 9 minus 64 tangent squared theta over 64. And, these cancel, you get secant squared minus, and we said this is an identity, so it's always equal to 1. So that, oops, sorry, off screen. Yeah. Right. So, and we were doing that in GeoGebra, I think, when we got interrupted. So maybe we should look at that. That's odd. Okay. So where is GeoGebra? It's right here. Oh, I got some. Oh, right. Yeah. Let me take us there, but we're not there at the moment. So where is GeoGebra? I want to close this out and go down here. Okay. Here's what was kind of interesting. I didn't know this before yesterday, that if you just put in the coordinate pair, but you write each coordinate as a function of the parameter. So 3 times secant t, comma 8 times tangent t. Boom, there's our hyperbola. So we didn't even have to say, curve. It knew that this was look at how it labels it. It labels it as parametric curve. Let's zoom out here, right? So there's our hyperbola, right? And I suppose we could make a look. So it's showing the asymptotes because it's trying to connect, subsequent dots, right? So there's a dot out here that connects with a dot down here to draw this line, which just happens to coincide almost exactly with the asymptotes. So it's sort of a lucky accident, I guess, maybe. Right. So, and we have our vertices at plus or minus 3. The transverse axis is going to be, oh, I see. This line segment here, can I say, yeah, give me this point and connect it to that point. Okay, that's the transverse axis. It's got length twice a, which would be 6 in this case. And the focus is out at square root of 70, what was it, 73? Yeah, 64 plus 9 is 73, right? Comma 0. So there's a focus, and there's some interesting reflection properties. Should we go to the book and see, remind ourselves what those interesting reflection properties are? So where is the book? Oh, I don't want this. I think I want this. Okay, and Sumatra. Okay, there's the book. And if we scroll up here, it says, yeah, if you have light rays emanating from one focus and bouncing off the other focus, or actually they're showing the reverse here, right? Light coming in pointed towards this focus. That's kind of small, isn't it? Okay, so you have radiation coming in directly aimed at focus 1 here. If it reflects off the hyperbola, it will be reflected back towards the other focus, right? No matter which direction it's coming in at, right? Can we demonstrate that in GeoGebra? That might be a bit of a challenge, although I'm always up for a challenge. Should we try it? I don't know. So let's make a line segment. I think I tried something like this before. It didn't work out too well, right? But if we make a line segment, oh, where am I? I don't see. Oh, there it is. Okay. So I want a line segment like this, right? And then, yeah, it helps to have see, it doesn't look right here. That's because the scale on the horizontal scale is obviously different from the vertical scale, right? In order to make those scales the same, I'd have to stretch it out like this. Oh, sorry. Okay. Oh, and I lost my, okay, that looks about right. So now if we were to reflect off of this, would it go to, well, let's draw the other focus in, right? So that's going to be negative square root of 73, comma 0. That's over here, right? And so I suppose I could be cheesy and just do this, right? Say I want to connect to where these things intersect. Oh, it's not allowing me to do that. So I want to get the point of intersection of this and that. Really? Oh, they're not finding the intersection point. Because, yeah, that's interesting because it's not really part of the graph. No, it won't do it. I suppose I could try to just put a point there. It won't even put a point. It puts okay nearby. Okay. I want a point right there and puts it over here. Oh, that's actually where I want it, isn't it? So it's not going to reflect off the, that was dumb. It's not going to reflect off the asymptote. It's going to reflect off the, yeah. All right. So does that look convincing? Like, the radiation coming in pointed directly at this focus will reflect off the surface. Well, it's not a surface, but you can imagine that there might be a surface there. It will reflect off this curve of the hyperbola, and the angle of incidence is equal to the angle of reflectance here. So it bounces back towards the other focus. And that's irrespective of where it comes in. So I could like draw another one, right? Here's one like this, coming in towards that focus, intersecting the hyperbola here, and then bouncing off at the angle of incidence equals the angle of reflectance. And yeah, that looks convincing to me, right? That this angle above J to the left is equal to this angle below J to the left, right? Okay. All right. So let's do another one. Sumatra, and here we go. So I think that was number 12. So how about number 24? So here we have one where we got to sort of do some work, right? So let me copy it over to the workbench, which is here. Okay. And it seems like we could zoom in a little on this, huh? Is that too much? That's too much. It's very sensitive, these phones. Okay. So I want to write, and I guess I want to tip this back a notch. Is that possible? Yeah. So I got this space here. So this is 5.4 number. So 5.4 number 24 is what we're doing. And the equation given here is x squared minus 3y squared plus 12 equals 0. So this is not in standard form, right? So to get standard form, I could subtract 12 from both sides, and I'd have x squared minus 3y squared equals negative 12. But I want a 1 over here, right? So I divide both sides by negative 12. And that's going to reverse, since I'm dividing by a negative, I'm going to reverse this difference. So that's going to give me y squared over 4, since 3 over 12 is 1/4, minus x squared over 12 equals positive 1, right? So that's standard form. And we see a is with y here, right? So a is 2, and b is the square root of 12, which is 2 times the square root of 3. Approximately 3.4. What's the focus? C is going to be equal to the square root of 4 plus 12, which is 4. That's kind of convenient, right? Right, because this is a squared plus b squared. So the transverse axis is on the y-axis now, right? And so if we're going to graph this, we're going to put the center in the middle, right? Because this is centered at the origin. And the transverse axis will go from -2 to +2 on the y-axis. This is the x-axis. And what is the box? Well, we want to go out to about 3.4, right? To get the box. So this is, 2 times the square root of 3, right? And I guess back in the negative direction as well, right? So this is the box. And the corners of the box are, this is -2 times the square root of 3, about -3.4. And so the box, somehow these rulers just go missing sometimes. Oh, here it is. So the asymptotes go through the diagonals of the box, right? And what's kind of interesting about this is you could draw an ellipse inside the box, and you could draw 2 different hyperbolas here, right? I mean, there's only one hyperbola for this equation, right? But think if you were to reverse this difference, you'd get the other hyperbola with the vertices on the other, on the x-intercept, right? But now we just want to sort of fake in, I say fake, because we're not being religiously correct about coordinate values. We just want to capture the essence of approaching the two asymptotes and then diverging from the asymptote in order to pick up the vertex and then heading towards the other asymptote, right? So there's our hyperbola. Where are the foci? Well, there's one up here at 4, and there's one down here at -4, right? So, a line, we choose pretty much this. So if we had a line headed towards this vertex, right? So it would have hit that focus. Instead, it bounces off the surface or the hyperbola, so that this angle is equal to this angle of incidence. And I know this is a curve, but near the point, it's nearly a straight line, right? So we can talk about angles here and there, which are equal, and then this line will bounce off that and hit this other focus. I don't know, so the transverse axis is from where to where? It's from 0, -2 to 0, or the other way around, either way, right? It's not directed really. It's just the line segment connecting these 2 points. All right, do we want to parameterize this? Yeah, well, we'd say it's secant squared minus tangent squared, right? Secant squared minus tangent squared. So we'd say y is equal to 2 secant. And actually, you can give, another parameter in here, like omega t. That would just change the speed at which you travel along the curve, right? Because it's still going to be true that you're going to have secant squared blah, minus tangent squared blah, is 1, right? So x is going to be 2√3 tangent. Then we have to have the same input here, right? And so this will parameterize the hyperbola in terms of t, where omega is just a parameter, right? Omega is not the guiding parameter. It's just it says how fast you're going. You can think of it as an angular velocity. All right. Okay, good. So that has used up yesterday's paper, which is good. So let's go on to today's paper and do another one. I think what we should do is skip on to shifted conics, right? We talked a little bit about those before. Yeah. So they've got some applications. Yeah, those are good. Again, you can talk about a cone of light. Sorry, I should be on the, where do these things come from? Okay. So where's Sumatra? It's here. Okay. So shifting graphs of equations. So back in section 2.6, we studied transformations of functions that have the effect of shifting the graph. In general, for any equation x and y, if we replace x by x minus h and or x plus h, that shifts it horizontally. And if y is replaced by y minus k or y plus k, which, if k is negative, then amounts to the same thing. The graph is shifted vertically And so the following box gives the details, right? And so here they're sort of describing it the way I wanted to describe it back in 2.6, which is actually replacing, doing the same thing to X to shift horizontally as you do to Y to shift vertically, right? So we start out with shifted ellipses. You just replace X. X is being squared here. So here, whoops, sorry, that wasn't quite, maybe I should shrink my box so I can see where we are, right? Right, so you see the X is replaced by X minus H. So instead of squaring X, we square X minus H. And same thing with Y, right? Okay. And so the unshifted conic is X squared over A squared plus Y squared over B squared equals 1. When you shift it, it's the exact same shape. The shape is not changed in any way. It's just shifted. I suppose that's a way, but it's the same shape in a different place. Okay, so sketching the graph of a shifted conic, basically you want to find the center point, then find the 4 extreme points, the vertices of the ellipse, and then find the shifted focus, and you can plot everything like that. Shifted parabolas, same thing. Shifted hyperbolas, pretty much the same thing, right? So let's just get right to the exercises and see how the general, oh, well, maybe we should need to talk about this. Yeah, we do need to talk about this. The general equation of a shifted conic. So what you see here is a quadratic polynomial in 2 variables, X and Y. So instead of just having either X squared or Y squared with the other variable not squared, here both X and Y appear as squares with coefficients, right? So the coefficient of X squared is A, the coefficient of Y squared is C. What happened to B? I don't know. They skipped over B. Maybe if we read this further, we'll find out why. So if you have the equation ax squared plus cy squared plus dx plus ey plus f equals 0, where a and c are not both 0, then we're going to have some kind of a conic, maybe? It could be if a and c have the same sign, and there are any points that are solutions, then those points will be on an ellipse. If A and C have opposite signs and there are any points that are solutions, then you'll have a hyperbola. If A is 0 or C is 0, then you'll have a parabola, right? But you may have a degenerate conic, that is one where there is no solution. So they say the general equation of a shifted conic is given by this expression involving parameters A, C, D, E, and F, where A and C are not both 0. If A and C were both 0, it'd be a straight line, right? So that's not a conic. So it's a parabola if A or C is 0. It's an ellipse if A or C have the same sign, or a circle if A and C are actually equal. And it's hyperbola if A and C have opposite signs. So here's an equation that leads to a degenerate conic. So shall we see why that is? Let's see why that is. So we'll go to paper and pencil for that, which is here. Okay. So the equation we have in mind here is 9x squared minus y squared. So A is 9, C is -1, D is 18, E is 6, and F is 0. Well, I guess we could say plus 0 equals 0, but F is, there could be another constant added in here. which in this case, that's 0, so we don't bother to write it. Okay, so the trick here is to complete the square for x and complete the square for y. So both, we need to complete the square for both. So to do that, we're going to factor out 9 from the two terms involving x and factor out -1 from the two terms involving y. Right, would you agree? Oops, I'm off screen. How'd that happen? I guess I need to tilt this down a notch. All right. All right, so let me give you a second to catch up with that. Sorry. So they give us this equation where they've, this is a general equation or the form of a general equation of a conic, which is quadratic in both x and y. And has, specified parameters. A is 9, C is -1, D is 18, E is 6, and F is 0. So F does not appear as a term. So my first step is to take the two terms involving x and factor out the leading coefficient. Then I also want to take the two terms involving y, and you could think of there being a 1 here. All right, so I'm factoring out a -1 if you like, or you can just put a minus sign. It amounts to the same thing, right? Okay, so now we got a quadratic in x and a quadratic in y. Inside the parentheses, the leading coefficient is 1, right? So what do we add to complete the square for x inside the parentheses? Well, the general rule is if the leading coefficient is 1, then you take half the coefficient of x and square it, and that's going to be 1, right? And do the similar thing. Half of 6 is 3. 3 squared is 9. But now I can't just write 0 on the right side, because what have I added to the left side by, well, this is kind of funny. In fact, it does amount to 0, doesn't it? Right? Because I've essentially added 9 times 1 and -1 times 9, which are opposites. And so I should, to be proper, I'd say 9 minus 9, right? But that's 0. So maybe that's just lucky. So we got a 0 over there. Okay, well, this is why it's degenerate. So this is 9 times the square of x plus 1 minus the square of y minus 3. Is that right? Equals 0. So what are the solutions to this equation? Yeah, this is kind of an interesting one. Would you not agree that, well, -1, 3 is a solution, right? So observe that -1, 3 is a solution. Are there other solutions? Yeah. In fact, if this difference is 0, that means this term is equal to this other term because we're saying that their difference is 0, right? So I can say 9 times x plus 1 squared must be equal to the square of y minus 3. And that means that 3, I'm going to equate square roots, but I want to get both of them, right? So I'm going to say plus or minus y minus 3. What kind of an equation? Well, this is actually two equations, one for the plus sign and one for the minus sign, right? And so maybe we should say that, either it's y minus 3 or it's 3 minus y, depending on whether you've got a plus sign or a minus sign there, right? In the first case, you're going to have the line y equals 3x plus 6. Is that right? I'd add 3 to both sides. So this is 3x plus 3 plus another 3 will give me 3x plus 6. Or if it's 3 minus y, then y is going to be equal to I want to say negative 3x, right? So 3x plus 3 equals 3 minus y. Subtract 3 from both sides, you get 3x equals negative y, or y equals negative 3x. Oh, so these are, so all points, so these are two lines, and all points on these two lines are solutions to the original equation. For instance, 0, 0 is on this line, right? If x equals 0, then y equals 0. That's a solution to this equation. That means it's a solution to the original equation. And sure enough, 0 plus minus 0 plus 0 plus 0 is 0 all day long, right? But let's graph these two lines and try to make sense out of what's going on. So where do they intersect? Well, they intersect at negative 1, 3. Is that obvious? Maybe not. Certainly if x equals negative 1, then y equals 3. Or if x equals negative 1 here, then negative 3 plus 6 is 3. So yeah, that is a point on both curves. And the slopes are 3 or negative 3, right? So negative 1, 3. The slope's 3 or negative 3. So I guess I'm going to scale by, maybe I should have drawn that further down, but it's 1, 2, 3, 3, and here's, I'm going to say 1, 2, 3. I'm going to scale at a different rate here. So this is 3. This is the y-axis and the x-axis. So negative 1, 3 is this point here. That's where these two lines intersect. This line has slope 3 and intercept 6. So it goes like this, huh? And the other one goes through the origin and also through this point. So this is the line y equals negative 3x, and this is the line y equals 3x plus 6, right? And that's the solution set to this original equation. And so what are we looking at here? It's kind of like, this is a conic section. So why do they call it degenerate? Because it's not a curve. If you think of the cone, think of this as being a cone, and we're taking the cross section right through the middle, right? So this is a cross section of a cone where you include this point where the tip of the cones meet, right? Two-sided cone tips of the, so if you cut through this point here, then you'll get these two straight lines, which are kind of like the asymptotes of a hyperbola. It's like a hyperbola that's collapsed onto its asymptotes. Okay, so there's a special case. And let's go back to the book. How are we doing? Yeah, time flies when you're having fun. Gotta find the book. Okay. So they do pretty much what I did. It's graphed in figure 8. Where's figure 8? Oh, over here. Right. So they didn't, I used a different scale on the vertical axis, so it looks like my lines are less steep, but it's the same graph, right? They intersect at negative 1, 3. This has a slope of negative 3. This has a slope of positive 3. And so what do they say? Because the equation looked like, at first glance, like the equation of a hyperbola, but in fact turned out to represent simply a pair of lines, we refer to this as a degenerate hyperbola. Degenerate ellipses and parabolas can also give rise when we complete the squares in an equation that seem to represent a conic. For example, this equation looks as if it should represent an ellipse. because the equations x squared, the coefficients of x squared and y squared have the same sign, but completing the square leads to this, where you see that you have a square, right? This square, that's got to be positive, right? The square of any real number is a positive, maybe 0. This is also a square, right? So we're adding 2 squares, so we're adding 2 positive numbers and getting a negative number. That's impossible. So in fact, this is a degenerate ellipse that has no solutions at all, right? So it's worse than the other one. All right, so with that, let's get into the exercises, and maybe let's look at number 12. Okay. So this is 5.5, 5 point, I don't know what section we're on anymore. Does it say in the margin here, conics, oh, 11.5 maybe, right? Well, 11.1 was parabolas, 11.2 was ellipses, 11.3 was hyperbola. So I think there's 11.4, number 12. Okay. So here comes the DocuCam, and let's line that up properly. So 11.4, number 12, where we see the equation 9x squared minus 54x. Okay, so the x terms are together. That's nice. Plus y squared plus 2y. Oh, that's nice. That'll be easy to complete the square for y. Plus 46 equals 0. Oh gosh, I'm using my phone as the DocuCam, and it's got some sort of Amber Alert going on it. I think that's what that was. I don't know. Okay. So we want to complete the square for x. To do that, we want to factor out the 9 first, right? And so 9 times 6 is 54. So we want to add something to complete the square there, right? Oh, sorry. We don't want to square the square, do we? Plus y squared plus 2y plus something will complete the square for y. And let's write negative 40. We'll subtract 46 from both sides, okay? So what do I add to complete the square for x? Well, we got inside the parentheses, we got a leading coefficient of 1s. Half of 6 is 3. 3 squared is 9. Half of 2 is 1. 1 squared is 1. So now what do I need to add to balance the equation, right? By adding 9 inside the parentheses here, I added 81 to the left side. By adding 1 inside the parentheses here, I just added 1. So I added 81 and 1, that's 82. I want to add 82 to the right side as well, right? To balance the equation. So now the equation is 9 times the square of x minus 3 plus the square of y plus 1. And what is that, 46, I think? No, 36. That's good, because that's a perfect square. That's nice. That'll work out nicely then. So I want a 1 over here for standard form, right? So I'm going to divide both sides by 36, and that gives me x minus 3 squared over 4 plus y plus 1 squared over 36 is equal to 1. So this is standard form for an ellipse centered at what, 3, -1, right? With semi-major axis 6, semi-major axis of length A equals 6, and semi-minor, semi means half, right? Semi-minor axis of length B You remember with the ellipse, we always say A is the bigger one, right? You don't have to, but that's what the book does. I tried to be consistent with the book. Okay, so, right. So centered at 3, -1. So where are the vertices? Well, they're going to be, so the semi-major axis is vertical, right? So we're going to go 6 up and 6 down. So the vertices of the major axis are, start at the center and go 6 up. You're going to be at 5, right? So you're going to be at 3, 5. Go 6 down, you'll be at 3, -7. And vertices of the minor axis at, so we're going to go 2 away from the center. So the center has x coordinate 3. So we're going to go 2 to the left of that and get 1, and 2 to the right of that and get 5, -1. So I think we're ready to draw the ellipse, right? So, try to set up your coordinate axes to correspond to the center and where these vertices are. So we want, y to stretch from +5 down to -7, and x to stretch from 1 to 5. So that seems like the action is all to the right, and kind of skewed downwards. So I'm going to set up my coordinate axes like so, and the x coordinates I want to go from 1 to 5. So I'm going to say here's 1, 2, 3, 4, 5. Those are perfectly evenly spaced hash marks. And then we want to go from -7 up to 5 on the y-axis, right? So here's 1, 2, 3, 4, 5, 6, 7 down, and 1, 2, 3, 4, 5. Almost made it there. And so the center point is at 3, -1. That's here, right? The major axis goes from 3, -7 to 3, 5. Right, so that's 6 up from the center and 6 down from the center. And then we're going to go 2 to the right of the center for the minor axis, and 2 to the left of the center. And then just draw a nice oval shape through those 4 points. Where's the focus? C is equal to the square root of a squared minus b squared. So in this case, that's going to be the square root of 32, 36 minus 4. And I guess that's 4 times the square root of 2, which is approximately, square root of 2 is about 1.4, so that'll be about 5.7 maybe. Close. And so we're going to go, let's see, does that work? Yeah, that's less than 6, right? But it's pretty close. So this is pretty eccentric, right? So we got to focus up here and a focus down here. Is there anything else to do here? We could talk about the parameterization. X would be, so take a look at the standard form, right? So we want this to be cosine squared plus sine squared equals 1. So let's say cosine squared t, we want that to be x minus 3 squared over 4. That says that x is equal to 3 plus 4 cosine t. You see that that works out? You take square roots, so you got cosine t is x minus 3 over 2. Oh, sorry. My bad. Over 2, huh? So this should be a 2. Right, and that's, so the equilibrium for x is 3, and it oscillates 2 up and 2 down, right? So this is doing that, right? With equilibrium 3 and amplitude 2, it's oscillating horizontally back and forth at the same time that y is going to, oscillate around -1 with amplitude 6. And so that gives the parameterization in terms of a parameter t. You can call the parameter whatever you like, right? There's no t-axis here, right? So we're not plotting t. We're using t. So we're going to say that when t is 0, where are we? We're at 5, -1, right? 3 plus 2, cosine of 0 is 1, sine of 0 is 0. So this is 5, -1, which is this point here, right? As you go quarter turn around the ellipse, cosine of pi over 2 is 0. So x is 3. Sine of pi over 2 is 1. So this is 5. And you're up here at the North Pole when t equals pi over 2. All right, and we can sort of keep going like that, right? At pi, that's a half turn around the ellipse. Cosine of pi is -1, so 3 minus 2 is 1. And you can see this would be -1 will be here when t equals pi. And then 3 pi over 2 is a 3/4 turn around the circle, around the ellipse, I guess, elongated circle. And cosine is 0, so we're at 3 again. Sine is -1, so we're at -7. And that's down here, right? Where t equals 3 pi over 2. And then at 2 pi, we're back home, right? Where we started, one complete orbit around the ellipse. All right, I guess we're out of time. So that kind of completes the topics for the course. I suppose we should have some homework on shifted conics. Did we get one in there? I don't think we did. So look for that. I'll give you until the end of the term to fix that one, or to do it, I guess. It's kind of like fixing it. Any questions before we quit? I'll be in my Math Science Study Center between 2 and 4 this afternoon. So if you're looking to ask me some questions, I'll be probably just twiddling my thumbs. So do come around if you like. Okay, I'm going to call it a wrap. And wish you all a very pleasant afternoon. See you tomorrow morning, huh?
Thank you, Professor.
Thank you.
Thank you.
Okay, I'll see you, Kevin. And Kevin, did you come in?
Yeah, I did.
Yeah. I haven't seen you in a while.
I've been busy with work and it's been like really tight on my schedule.
Oh, I'm sorry. I know it's a lot of people have that problem.
Yeah, it's okay. It was until last week when I came by and I started looking at everything.
Uh-huh. Okay, well, I hope you can get enough trigonometry to move on. We'll see.
All right, then,
Meanwhile-
thank you.
All right, thank you. Bye-bye, everybody.